Hello all, this is Shatabdi Acharya from Vedang Institute of Technology. In the previous video, we have taken up the module for bonding in solids, and there we were discussing about covalent bonds and metallic bonds. So we ended that lecture with a question. Second. Out of Na and Fe, which has more metallic bonding or greater metallic bonding and Y. Okay. So this was our question. We were discussing about metallic bonding. So before taking up this question, there are two key factors you need to understand for understanding the concept behind this. One is screening effect, which is otherwise known as shielding effect. Secondly, effective nuclear charge. Okay, these were the two concepts you need to understand for better understanding this question. Okay, so let's start off. See, if I'm saying screening effect, now imagine an atom which has a nucleus and orbitals. Okay, basically whatever physical or chemical properties or reactions an atom undergoes is because of two interactions or interaction between the nucleus and the outermost shell. Okay, obviously the intervening orbitals are important to us. The penultimate and antipenultimate orbitals are definitely important to us, but the net result is because of interaction between this nucleus and the outermost shell, right? Okay, so let us say I'm standing here, I have to reach to a person standing at the other end. Okay, so with what effectiveness or with what speed am I able to reach to that person depends upon the path to which I have to cross, right? So if that path is full of hurdles, then it will be very difficult for me to reach to the person at the other end, or my effectiveness for reaching the other person is comparatively hampered, right? Okay, now relate that concept to atoms here. For example, the nucleus has to reach the outermost shell. Then in order to reach, it has to come across the antipenultimate as well as the penultimate shell. Now, all shell means electrons. Obviously, they have electrons in between them. So, obviously, nucleus will have an attractive force with these electrons as well, right? And these electrons in between them, there will be repulsive forces. Excuse me. So these repulsive forces in between these electrons will kind of push the outermost electrons further away. Now the distance, this distance will be further increased, right? If the distance is increased, then the effective nuclear charge will gradually decrease, right? The nuclear charge with which, or the nuclear force with which the nucleus was about to attract that electron will decrease. Now the amount of nuclear charge which is actually falling on the outermost electron is called as the effective nuclear charge, and it is related to, or it is dependent upon, how many electrons are present on its way. Okay, what is the density of electrons these nucleus has to come across to reach to the electron at the other end? Got it? So these electrons act as a barrier. Basically they act as a shield that protect the outermost electron from the effect of the nucleus, right? So this hindrance or this diminishing of nuclear charge on the outermost shell is called as screening effect or shielding effect. The intervening electrons, they act as a shield, okay? They protect it, they act as a screen which prevents the actual nuclear charge which was expected to fall on the nucleus, that is getting gradually decreased, right? The total net nuclear charge which is falling on the electron is lesser than that expected. Got it? So this effect is called screening effect, and because of screening effect, the nuclear charge which is the resultant nuclear charge which is falling on the outermost electron is called as the effective nuclear charge. So I can say effective nuclear charge is inversely proportional to screening effect. Effective nuclear charge is inversely proportional to screening effect. Okay, now let us say, if I am saying this, like basically the screening effect is because of the intervening electrons. Electrons are present in orbitals. Suppose I have s, p, d, f orbitals. Now, the question arises, will s, p, d and f orbitals show the equal amount of shielding effect, or the amount of shielding effect depends upon the shape and size or any factors? Obviously, we know the shape of s orbital is spherical. The shape of p orbital is dumbbell. That of d is double dumbbell. And f is diffuse or very complex shaped. Right, which is a fundamental shape we can say. Okay, so the shape of SPDF varies. Now consider the nucleus here. For example, the nucleus is surrounded by s orbital which is spherically symmetrical. Now this orbital which is symmetrical, it surrounds the nucleus uniformly, right? So the screening effect or the shielding effect of that particular symmetrical orbital will be comparatively higher than the unsymmetrical ones. So I can say s orbital shows maximum screening effect. S orbital shows maximum screening effect. Now, when we move from P towards F, what happens? The shape gradually starts becoming more and more diffused. So, due to this greater diffuse structure, what happens? The screening effect or shielding effect tends to decrease gradually when we move from P to D to F. So, the order becomes S has maximum shielding effect, then P, then D, and finally the least shielding effect is shown by F orbital. Next is s orbital can be of many types, for example 2s, 3s, 4s, 5s, so on. Same is the case for P, D and F also. Now, will all the s orbitals, all the P, D and F orbitals show the same screening effect, or will they somehow depend upon the distance? Obviously, if I am saying 2s, 3s, 4s, I am comparing between these three, sorry. Let's say 2s2, 3s2 and 4s2 we are comparing. So, the two electrons which are present on the 2s orbital, the 2s has smaller size. So, the two electrons which are present on the 2s orbitals are comparatively in a compact or a concentrated area. So, their effect or their interaction with the nucleus will be maximum. Gradually, when the size goes on increasing, the area where the electrons are spread out increases. As a result, the effectiveness will decrease. So, 2s being smaller in size show maximum shielding effect among these three. So, the shielding effect varies as 2s, 3s, 4s. So, the screening effect is dependent upon two factors here. One is the shape, second is the size. Okay, shape diffused, screening effect less. Size greater, screening effect less. Okay, so now coming to my question, out of Na and Fe, what happens which has more metallic bonding? So if I say in case of Na, the s electrons are filled and the s electrons being closer to the nucleus are held very tightly. As a result, they are not free, they won't be allowed to self interact. But in case of iron, Fe, what happens? The d electrons are filled. Due to lesser screening effect, greater size, what happens? the effective nuclear charge on them will be comparatively lesser, as a result of which their interaction will be maximum. Okay, so metallic bonding in case of iron is maximum, and that in case of sodium is less, and that's why sodium metals are very soft, they can even be cut with a knife. Okay, that's the reason, because of weaker metallic bonding, and iron metal is very hard because of very strong metallic bonding, right? Okay. Now, if I move on to the next concept which we had is bond enthalpy. Okay, so the next subtopic is what I said is bond enthalpy is related to bond energy. So basically, bond energy means amount of energy required to break a bond. Okay, whichever bond it is, ionic bond, covalent bond, metallic bond, whichever it is, the amount of energy required to break a bond, or in other words, I can say amount of energy liberated when a bond is formed. Okay, so stronger the bond, greater will be the bond enthalpy. And if I see the order, then ionic bond is a very strong bond. So the bond enthalpy for ionic bond will be maximum, followed by covalent bond, and least will be metallic. Understood? So this will be the order of bond enthalpy for ionic, covalent and metallic bonding. Moving on to the last part, which is secondary bonds. Now, what I'm saying, when I'm saying secondary bonds, then there will be some primary bonds also. So these kind of hydrogen bond, these kind of ionic bond, covalent bond and metallic bonds, they form the primary bond category. Now, if I move on to secondary bonds, these are some of the additional bonds the additional bonds formed along with the primary bond. Okay. Suppose I'm taking the example of the formation of HF, hydrofluoric acid. Okay. How it is formed? There is a covalent interaction between H and F. Yes. Now, when this HF is present in a crystal lattice, then there will be, let's say, many molecules of HF present around them. So, there will be direct bond between one hydrogen and one fluorine. But what happens? Fluorine is highly electronegative. So, what it will do, when another electropositive atom is present in its closer proximity, it will tend to interact with that also with a very minute force, very feeble force, very weak force. That force of attraction which develops between an electronegative atom and hydrogen of the other atom is termed as hydrogen bonding. This is our secondary interaction. Sorry. This is a secondary interaction, which is along with a primary interaction, the another bond is developed, which with a very weak bond is developed, that is called as secondary bond. One type of secondary bond is hydrogen bond. Next thing, if I am saying, suppose there are methane molecules closer to each other. So basically carbon at the center and 4 hydrogen atoms, there are electron densities among themselves, there are nucleuses also. So one methane will be somehow attracted to another methane by a very feeble force of attraction. Like there is a force of attraction which exists between molecules together when they are at closer proximity, and that bond is called as the van der Waals force. Van der Waals force, which is again a type of secondary interaction. There is other forces like London dispersion forces, dipole-dipole interactions. So these are some kind of the secondary bonds which are existing between or existing along with the primary bonds. So the bonds which are present along with the primary bonds, the additional bonds which are present, they are termed as secondary bonds. What are the types of secondary bonds? One is hydrogen bonding. Next is van der Waals forces. Third is dipole-dipole interaction. Next is London dispersion forces. And remember, secondary bonds are very weak as compared to primary bonds. So this brings us to the end of the chapter bonding in solids. In the next video, we will take up another chapter. Thank you for watching.